Okay, so we're rolling the die 120 times. How many can we expect it to be a 6? 20 times? And you're figuring that out because why?
Because you multiply it by 120.
Multiply what by 120?
1 over 6 is the possibility of 6.
Okay, so what you guys just proved here is that this entire concept of expectation is pretty intuitive. Okay? That's exactly what we needed to do. In order to figure this out, we would expect it to end up with about 20 sixes because the probability of getting 1 6 is 1 out of 6. And if we're doing that 120 times, you're multiplying by 120 by 1/6. Okay? So we would expect 120 rolls. This concept, okay, for one thing, is not guaranteed. As with anything, whenever we're dealing with theoretical probabilities versus experimental probabilities, which actually rolling the die 120 times and counting them would be experimental. Here we're talking about theoretical probability. Theoretically, we should end up with 20. Okay? So this is the expectation. If we have n trials of an experiment and the event has a probability of p, then we can expect n times p to give us the number of times that event will occur. Okay? That's why we say, you know, if you're flipping a coin 100 times, you're probably going to get about 50 heads. Because you have a 1/2 probability times 100, that's 50. Okay? So that's the real basic concept behind what we're going to look at today. Now, obviously, we're going to deal with more complex situations than just rolling a die. All right? For example, and we're also going to learn some terminology related to switch on me. Got the pinwheel of death here. I have a feeling it's about to crash. I just went get that. Okay.
The rest of the class, up to we have to leave.
Yes.
What time do we leave today?
When the bell rings.
Now, while this is deciding whether or not it's going to cooperate, what we're talking about when we're talking about expectation is we're talking about actually a mean outcome. On average, we can expect this much, okay? And they'll actually use the letter mu to represent this, okay? And that mu of, yeah, we crashed. Okay, let's bring that back up here. It's going to be the sum from I equals 1 to n of each probability, okay, outcome. All right? So, each outcome, remember those outcomes, the discrete random variables, we have different numerical values for that, and each one of those is going to have a probability. So we're dealing with a probability distribution, and the expected outcome is going to be the sum of those, okay? And again, that's going to be the mean outcome. Now, as you can expect, the more trials you run, the closer to that mean you'll probably end up at. Okay? For example, you know, you might flip a coin 10 times and get 9 heads. All right? But if you flip a coin 90 times, you're going to get closer, most likely, to a 50-50 split. Okay? No, we don't need that. Let's look at this. There we go. We have the mean result. So here you saw what I wrote up on the board there. Okay? It's the sum of all of the values times their probabilities. Okay? And that we could call the expectation, or sometimes you'll see it referred to as expected value. Okay? Here's an example that we could look at. We have a dairy farmer estimates that throughout the year, the farm's cows will produce about 25,000 gallons of milk. But the price doesn't stay the same all the time. Okay, the price will fluctuate throughout the year. Because of variation in the market price of milk and the cost of feeding the cows, the profit per gallon may vary with the probabilities given in this table. So we're going to estimate the profit on the 25,000 gallons. Okay, so you can see here, we're going to make a profit of $1.10 a gallon 30% of the time. We're going to make a profit of 90 cents a gallon 38% of the time. There's actually going to be 4% of the time where we just break even. Okay, we're just producing so our milk, our cows don't dry up and we keep our customers happy. We're not actually making any profit, and in fact there is 2% of the time where we're actually losing a little bit. Okay, but on average, what are we going to make? Okay, so the mean here, the mean expected value, or you could say E of x, sorry, not sigma, E of x is the sum of each value times its probability. Okay, so $1.10 times 0.3 is going to be 0.33. Okay, 90 cents times 0.38 is what? 27326, 0.326. Is that right?
Yeah, 342.
342? Yeah. I'll trust the calculator. All right. And then there, 0.7 times 0.2, 0.14. Okay. Here we're going to have 0.024. That's 0. And then finally, we're actually going to have minus 200ths times 0.1, so it's 0.002. Okay? So, in the end, what is he going to expect?
83%.
Wait, what is it?
Well, I added them all up and I got 0.834.
0.834. Okay. So now, finding that is good. We do want to make sure that we can interpret it properly. What does that actually mean?
They'll have profit.
On 83% of the time.
No. We're not. It's not that we're going to have profit 83% of the time. We're actually going to have profit.
Average price would be
average profit per gallon, we need to multiply.
Oh, that's-
There we go. That's the average profit per gallon, okay?
Multiply by
So
25.
83.4 cents per gallon is going to be our mean profit or our expected profit over the course of the whole year. Now, why might that be helpful?
So he
Because you
estimate.
can plan ahead, right?
So you can
He can plan ahead.
And like have more milk. No, that doesn't help.
Yeah, he's maxed out at 25,000 gallons of milk, but what does that give him for the year?
Oh, he an overall budget that he has to spend.
There you go. He's got his total profit now for the year, so now he can create a budget for that profit. All right, maybe he needs some new equipment, or maybe, obviously he has his living expenses. He can set his salary, or maybe he can now afford to hire on another worker.
So do you multiply that by
Okay.
25,000?
Yeah.
Yeah, we would multiply the 0.834 times the 25,000, and the total profit for the year, or the expected profit for the year, we understand that, would be how much?
208.50.
$208,050, okay?
No, like 20,850.
Oh, 20,850, okay. Yeah, that makes a lot more sense. Okay, $20,850, okay? So if he needs some new equipment and it's gonna cost, $10,000, now he knows he has another $10,000 on top of that he could do something else with, or whatever, okay? You guys get the idea. But that's gonna be his profit for the year, on average, okay? So, does that make sense?
Yes.
Okay, now that's a practical application, and obviously with, you may not be a dairy farmer, but you will deal with other things where you're gonna have fluctuating expenses, fluctuating income, and on average, you're gonna need to figure out what to expect, okay? Nonprofit organizations have to do this all the time because they usually get a big influx of money near the end of the year because people want to make sure it makes it on this year's tax return. Okay, but then other parts of the year are really low, or maybe they have certain events that bring in lots of money. Well, they've got to try to estimate how much they're going to have over the course of an entire year. So you have all kinds of different things like this. And this is the kind of thing where you're getting these percentages probably based on history. Okay? What has historically happened? We've been able to get this percent of the time and whatnot. So there's a little bit of inductive reasoning going on there. Okay? Now, another application of this, okay, is in the realm of what's known as game theory. It's kind of interesting. Game theory, as Dr. Gleek talked about game
Yeah.
theory a lot,
we talked about this in this class
And-
before.
zero-sum games and stuff
Yeah.
like that. Okay.
Yeah.
Believe it or not, game theory it's not all about games. It's about just any time that you have two parties or multiple parties involved trying to come out with a solution that works for everybody. Okay? And fairness, a game is fair if the expected outcome is 0. You might say, well, how in the world does that work? How would it work to have an expected outcome of 0?
No one has an
One time
advantage
over
over
one.
the other guy.
Exactly. An expected value that's not 0 would mean one side has an advantage over the other, or is expected to come out ahead. All right? If you do the expected value on any casino game, it's going to be against you. Okay? That's how they get all the shiny lights in big buildings. All right? It's not because lots of people are winning. The expected value is in the negative for you. Okay? So it's not a fair game. You can create different games and you can make them fair by doing the math. A lot of the board games you might play, or video games or whatnot, you'll look at, you know, it looks like one player has this real advantage, but then he has this one weakness, and this other player has a advantage that will exploit that weakness. And really what it comes down to is they're the same statistically. If both people play a perfect game, it's going to come out to a 50-50 split. So it really what it does is it puts it in the hands of the users to play properly, or to play the best strategy, okay, in order to try to win. And a good game will do that. It won't have built-in bias for one side or the other, okay? You guys ever play the game Risk?
Yeah.
Okay. In the game of Risk, you're trying to take over the world. The attacker gets to roll 3 dice. The defender only gets to roll 2 dice. But if there's a tie, the defense wins. All right, so you see, oh, they get to roll 3 dice. They have a better chance of winning. But it really balances out, okay, and I don't know the exact numbers on the probabilities or the expected value there, but because the tie goes to the defender, them having only 2 dice evens the playing field a lot, okay? Now, here's a little game, Chuck-a-Luck. I didn't come up with this, but here we have a game where we're going to pick a number from 1 to 6, and we're going to roll 3 dice, okay? If our number comes up all 3 times, we're going to win $3. If it comes up twice, we're going to win $2. If it only comes up once, we're going to win $1. Otherwise, we lose $1. Okay? We have to pay them $1. All right? So, we have different possibilities, and one of the things that can be helpful is to make yourself a little table, the payoff and the probability, or this could be your X values here, your values of our discrete random variable, okay? Or I'm sorry, that wouldn't be. These would be your X values. This is the payoff for each X value, okay? So if we roll all 3 times, we're going to gain $3. We roll our number twice, we get $2. We roll it 1 time, we get $1. And if we don't get our number at all, we lose $1. So those are the payoffs, or the expectation for each one. Okay? However, are these equally likely?
No.
No.
No. How would we figure out the probabilities on this one?
1 and 6.
Out of 3 times.
1 and 36.
0 is most likely though.
You think 0 is most likely?
Yeah.
1.
Yeah, 0 is the most likely because it's like 4.
5 multiplied by
4. It's 5 and 6.
How would we figure it out, though?
It's
Do you divide out of
so
18?
any other number, any number other than yours,
Mm-hmm.
will be
5 out of 6 times, right?
yeah. Yeah.
Okay.
so the first
But-
one is 1.
5, 6, 5, 6.
No, that's wrong.
5, 6, 5, 6, 5, 6. That's the
Yeah.
probability of getting none of them, right?
And then 1, 6, 1, 6,
The
1, 6.
first one?
Yes.
That's the probability of getting of all 3 of them. How do we get the middle ones, though?
What's the
1, 6
middle?
times 1, 6 times 5, 6.
Yeah.
Okay. But how many ways can that happen?
5, 6, 1, 6, 1, 6, 1, 6, 5, 6.
Yeah.
1, 6.
Do you guys recognize this situation?
Yeah.
What do we need to use?
Permutation.
No, combination.
It involves combinations, but what's the overall thing? We have 2 possibilities.
Distinguishable for no.
We have 2 possibilities. It's a repeated event,
No.
and they're
It's
independent.
like the chart.
That's tree
Oh,
thing.
Tree.
I don't know what it's called.
Mutually exclusive.
That's what I was.
They're independent,
I can't think of the word.
this.
repeated independent events,
What is that? Yeah, this is what we're doing our review project.
binomial probability.
What is that?
We talked about it last year. We have the binomial expansion.
Probability was to death.
Okay. Well, here's how it goes, okay? And you'll see even more of it in a couple of the presentations, all right? We have two possibilities. We either roll the number we picked, which is a 1 in 6 chance, or we don't roll the number we picked. That's a 5 in 6 chance. These have to be complements of each other. They have to add up to 1. And we're rolling 3 dice. So this is why it's to the 3rd power. Then you're just using the binomial expansion. Okay? Now you guys were right about the first, getting all 3 your number and getting all 3 not your number. And the reason why you were right is because if you remember Pascal's triangle, the beginning and the end of each row was a 1. Okay? But if you recall, the 3rd row here is 1, 3, 3, 1. And that's where you guys had the right idea to figure out this probability here, okay? This is 1/6 to the 3rd power, and this is 5/6 to the 3rd power, okay? This is the probability of getting your number twice, okay?
And what is the?
So that's 1/6 squared times 5/6. You're going to not get your number once, right? But I asked how many ways could that happen? Well, that's where Pascal's triangle comes into play. It's going to happen 3 different ways. Now, you can figure that out because you have 3 is the power you're raising it to, and you're going to do a combination. And remember, it has the same number you're choosing as this exponent here. Okay? I know we haven't hit the review of binomial theorem yet, but you guys will see Thursday or Friday how that works. Okay? Our next one is going to be 3 choose 2, which is also equal to 3. But now we're only getting our number once, and we're getting the other number, some other number, twice. Okay? So there are those probabilities. Okay? Is everyone with me on this? Okay? Does it look vaguely familiar at least?
Yes.
Yeah.
Alright, it should. Alright, maybe
Fancy.
you've psychologically blocked out that traumatic period in your life or something. But you have PTSD after the probability. Alright, so anyways, here are those probabilities plugged in. Okay? So now, how would we find the expected payout?
Multiply the 3 times you win, the sum of those by the money you
Wait,
pay.
multiply what by what?
So payout by probability.
Yeah, multiply the payoff by the probability. We're going to gain $3 this often.
So that's
Alright, so that's less than, or 1.4 cents. Okay, or 0.014.
yeah.
We're going to gain $2 almost 7% of the time. So again, we multiply that. And we multiply each one, okay? And then what are we going to do with those 4 numbers?
Add them up.
We're going to add those up, okay? We're going to add these up. So, what do we get when we add these up?
Is it always going to be the same number in every case?
It's not always going to be 0. it's only 0 if the game is
It's fair.
fair. So this will help us answer the
Negative.
Oh,
question.
so this is
Negative
gonna tell you if the
points.
game is fair or
No,
not.
it's not fair.
Negative
It's
point
not
oh seven
fair.
So negative 0.07 what?
9.
9?
The game is not in your
Okay.
favor.
So the game is not,
It's not
in your
balanced,
favor.
but it's not in your
Okay.
favor.
What a surprise.
you are more likely to lose 8 cents about every time you play the game. Okay? If we're the one running the game, we could expect to make 8 cents for every person who plays the game. So we buy a bunch of cheap prizes and get hundreds of people to play our game, and then we make money.
Simple math.
Okay?
Boring.
So, the odds are never in your favor. If you go to a fair or you go to a carnival or something,
Don't bother.
I don't know how they do those
The-
games where they like
Don't touch me.
ask like, oh, I can guess your weight, your birth year.
oh, the probabilities on those are actually huge because you have to usually be within what, like 2 months?
Yeah, it's like 2 months, 5
So
pounds.
basically, 2 months. There's only 12 months, and if you get 2 months either way, you have a 5-month window that you got to guess.
It's not in your
So that one's actually slightly in your favor, the month one.
Very nice.
The 5 pounds, I mean, they practice and they can kind of get a sense of how much. But I mean, if you think about 5 pounds, they have an 11-pound window to get inside. And then age, what's age? Like, how many years do they usually give you on those? A couple years. But anyways, I mean, they give themselves a window of ranges where they could guess. So some people are really good at it. I'd be terrible at it. But, that actually is one though where the month one is in your favor slightly, because they have a 5-month window, so you have a 7 out of 12 chance of winning.
Wait, what if the game is you already paid $1, and then if you get it once, you will gain $1, but you actually don't get anything.
Yeah,
So you get
that
a 0.
that you can. That's where you have to consider the payoff. The payoff would be like here, you're paying $1 to play, and you just lose that $1.
Yes.
Here, they're giving you $2 back, so you get your original $1 back to break even, and then you win $1.
Okay.
So, you know,
So it's actually.
so you'd have to be
2,
careful.
3, and $4.
Huh?
It's actually 2, 3, and $4.
Well, but that's not the payoff. That's how much they hand
Yeah,
out,
yeah,
but that's not how much you actually win.
yeah.
If that makes sense. Okay. All right. So, any questions about this? Kind of interesting topic, and actually, this is one area that people have
Fixing
done some IAs. You have to get a little creative with it, but you can do an IA on this. You could do searching expected values of different games and seeing which would be the best to play or whatnot. But that's a possibility. Okay. Let me stop this.